Hello, everyone. I'm Brennan Jones. I'm a PhD candidate at the University of Calgary. Today, I'm going to present our work on behalf of my co-authors on FeetBack, Augmenting Robotic Telepresence with Haptic Feedback on the Feet. So I'll start with a bit of motivation. Telepresence robots allow people to be present in and have mobility in a distant location, and they provide opportunities for people to participate in activities in distant spaces that they would otherwise not be able to enjoy. However, it can be difficult to remain aware of one's surroundings and easy to accidentally bump into people or things in crowded environments such as conferences. To address this challenge, we designed a haptic feedback system called FeetBack. When driving a telepresence robot, users place their feet inside the FeetBack system and receive haptic feedback on their feet when approaching and hitting obstacles in the remote space. The goal is to provide users with additional non-visual feedback of what is around them in the remote space, with the hopes of enhancing awareness, boosting sense of presence, and helping them make better navigation decisions. So a little bit of related work. Telepresence robots have been studied in contexts such as work meetings, academic conferences, museum tours, homeschooling, and in the outdoors. Augmentations have also been built and explored, such as 360-degree cameras, VR usage, and AR avatars. However, we're not aware of many existing augmentations that make use of haptic feedback. Haptic feedback has been explored in other contexts, such as in the use of telerobotics for hand manipulation tasks. What we're interested in is A, applying haptic feedback to the feet, and B, understanding how this haptic feedback can be used to support navigating and operating a telepresence robot and in supporting the feeling of presence while doing so. So we created FeetBack by extending a commercial telepresence robot called the Beam Plus, created by Suitable Technologies. We extended this robot with a purpose-built sensor ring consisting of 12 ultrasonic range sensors. These sensors surround the robot in 360 degrees, providing a measurement and mapping of nearby obstacles, their distances from the base of the robot, and their approximate orientation with respect to the robot. This data is then sent across a network to the FeetBack platform, which then uses it to provide corresponding haptic feedback. The FeetBack platform is composed of a high-density wood and aluminum foot platform to which actuator blocks are attached. Users remove their shoes and place their feet within the platform. Based on the distance sensors on the robot sensor ring, users receive directional vibration cues when the object is sensed, and the vibration frequency increases as the object gets closer to the robot. Once an object is in a predetermined collision range from the robot, a solenoid on the corresponding side of the FeetBack platform triggers, providing a soft but noticeable impact to the user's feet. So with this system, we conducted two studies. One, a study in a virtual environment as an early investigation, and the second, a study looking at telepresence usage in real public environments. So for the first study, it was a within subjects experiment where we had 19 participants in total. We created a virtual simulation closely mimicking the visual cues and gamepad-based control of an actual telepresence robot in a large virtual indoor space with obstacles and moving people. Participants were asked to navigate from point A to point B as quickly as possible while hitting as few things as possible. And they're given an overhead map of the space and told where they had to go, but they weren't told where they currently were. In this study, we compared driving with the haptic feedback provided by FeetBack to driving without in two similarly laid out environments. For more details on our procedure and analysis, please see our paper. Very briefly, here's what we found. So overall, FeetBack led to higher overall feelings of spatial presence, as well as overall higher feelings of realism. In addition, participants said they moved around the space more cautiously with haptic feedback. However, some found the haptic feedback to be distracting or stressful. Others said that their investment and immersion increased with haptic feedback. So for study 2, we looked into real telepresence situations. Here we recruited 17 new participants and had them drive a telepresence robot around our university campus in the middle of the day when there was many people around. And they completed a series of 8 tasks where half were done with FeetBack and the other half without. So our goal here was to provide opportunities for social interactions as well as maneuvering around confined, crowded, as well as wide open spaces. I'll give a couple examples of the tasks that they had to complete. So in one of the tasks, participants had to navigate an area with chairs and desks near a cafe to find a specific person. And in another task, participants had to go to the student advisor's office, find an advisor, and ask about course offerings in our department. After completing these tasks, participants completed questionnaires and we interviewed them as well. For more details on our data collection and analysis, please see our paper. Here's what we found. Most participants said that they found FeetBack to be useful in understanding the remote environment better. They said they could feel if they're getting too close to obstacles and if somebody was moving behind or next to the robot, especially when they couldn't see them on screen. So as an example, P13 said, "I think having vibrations helped me. When I was taking the turn, I didn't realize I was going to hit the chair. So having a vibration on my right foot made my eyes go near to the right side of the screen. And then I got to know that there's a chair and I have to move." The feedback also had clear effects on the behavior of participants. For some, it meant changing their behavior immediately, particularly to avoid situations like this. For example, P10 said, "The kick really helped me in providing feedback that you're getting way too close to that object and that you'll hit it." However, participants felt that the usefulness of feedback varied with the context of the task that they're performing. So for example, it was useful for maneuvering around tight spaces, but less useful when you're in a hallway and you have 2 walls on your left and your right side, and the feedback is triggering all the time. So for example, P5 said, "On the ramp, the robot was not in danger, but it kept vibrating, so ultimately I ignored the feedback." So to conclude this study, feedback had a positive effect on user behavior in terms of improved awareness and subsequently more cautious driving. However, there were times when the feedback was repetitive, unnecessary, or did not provide any new actionable information. This suggests value in context-dependent systems that can have a better understanding of the specific situation. So to conclude, our contributions are, we built a foot-based haptic feedback system for telepresence robots, as well as a sensoring, and conducted 2 studies with this system. Thank you very much. Here's our contact information.